I put this up earlier. If you want to follow along, I want to do this more workshop style, so you don't just sit and listen. Then grab that Docker container, singlet/x8664 workshop. And I'm going to have a copy. Or it's not coronavirus. Well, I don't know, actually. I had a chest infection. Yeah, so I'm going to leave that up for a little bit to, if you want to pull that, you can clone the Git repository if you want to do it on hard mode, but the easy one is rather just to pull that Docker container. All right, so just a brief introduction. Like Hex Coffee was something we started about 10 years ago, just as an informal meetup for security people. And then amazingly, people in Cape Town, I see some of you are here, and now London ran that thing regularly, and it's pretty good. And then it got restarted in Johannesburg. But the problem for someone like me who's got kids is it's really hard to give up Saturdays to leave and go do those things. So I want to see if maybe we can do some during work hours on occasion. And this is not affiliated to a company or anything like that. This is just free sharing of security nerdery. So if any of you want to be up for doing one of these virtual sessions, I think that would be cool. And we do one next week, we do one 3 months from now, I don't know, something like that. And we can learn as we go along how to do these virtual sessions. So it's just a little bit about Hex Coffee. Okay, and then my name is Dominic White. I'm at Singe on Twitter. I work for a company called SensePost. We're owned by Orange Cyber Defense. Anyway, if you want to mail abuse at me, it's dominic@sensepost.com. Okay, so the reason I wanted to look at x86-64 and the reason you might want to is it's useful to understand what's actually executing. So what got me into it was I was writing stuff, trying to write performance stuff in Rust and Golang. And was confused by how what looked like the same code was executing very differently. And it's just useful to understand how the stuff works. It's a layer I've kind of avoided for a little while, and I wanted to get into it. And then it's also just useful knowing like what the compiler is doing. And I think lots of people think the compiler is the all-knowing God, but actually the compiler isn't always right. And then a lot of hacker stuff either revolves around reversing or leaked shell codes. So you have a much better idea of what that stuff's doing if you're understanding how ELF works, how the linker works, what opcodes look like, all of that stuff. So that's the main reason of why. Okay, so let's jump into it. I just want to check something for participants that just joined. That's the Docker container you need to pull if you want to follow along with this. Probably easiest if you screenshot that so that I can move along. Oh, 3, 2, 1. Okay. So when you compile something at a really simplistic level, you write some C code that gets compiled into assembly. That's your .o file. The assembly then gets linked into a binary, either linked with libraries on your system or just turned into an ELF file. Or depending on what operating system it is, might do things like that. So the part we're going to look at is mostly the assembly. We're going to write the assembly that's going to then be linked and turned into a binary. Okay, so I want to kind of make it quite practical. I like that stuff more than just lots of slides. So if you've run the Docker container, you should get something that looks a little like this. Just a plain old Docker container, and inside there you'll see a couple of directories with stuff in. Yeah, so if you're having trouble with that, maybe ask in the Discord channel or in chat here, and others can help. Okay, so what I wanted to do is start off with something super simple. So there's a file called exit_ret.f, which is like probably the simplest ASM that I could put together, and I thought we could introduce the concepts. All right, so for this kind of two flavors of assembly, there's Intel and AT&T. I'm using the AT&T stuff. There seems to be lots of hate towards it. The reason I'm using it is because most of the tools use it by default. Some things support, well, most things will support switching to Intel. If you did the stuff at university, the main difference between Intel and AT&T we kind of need to care about now is the arguments are reversed. So in the AT&T syntax, if it says move 0 into RAX, that's from 0 to RAX, whereas Intel's the other way around. If you don't know what I'm talking about, then ignore it. Okay, so executable files got a couple of sections in it, an L file in this case. So there's a text section, which is the code section, we say that. And then we say, let's expose one of our functions externally so that things can call into it. So calling that the main function. And then we've got a label. These things are called labels, called main. And then it's doing two really simple things. It's moving the value 0. So it's like a put 0 into a register called RAX. So this is 64-bit. So RAX is a 64-bit register, and RAX is typically where return codes end up. And then we're returning. So it's like a super simple piece of assembly. Okay, so if we want to then compile that or build it, there's a tool, AS is the assembler. So you say AS and you say, what do I want to output it as? Well, let's make something called exitret.o. And I want you to assemble exitret.s, which is that assembly file. So when I do that, it assembles it, and you can see it's now created an additional file called exitret-o. And then if you want to link it so that you can get a binary, use not ln, ld -o. We're going to call it exitret is the name of the binary, and then we just give it that object file there. It gives this error. I'll go into what that's doing just now. But we've now, if we look at this, you'll see we've got three files: the original assembly file, the assembled object, and then the resulting binary. All right, and we can run that like a normal Unix binary, and we get a seg fault, which is on purpose, and I'll tell you why in a moment. Okay, wait, let me switch back to some slides here. Okay, so just to go over what we just did with a little bit of slidage. So there's different sections in a file. Typically, you've got the code stuff, and you've got some initialized and uninitialized data, the data section and the BSS section. On your computer, you've got the executable gets loaded into memory, and then there's a heap on top of it, and the stack is above it. So people often say, and just confuse the hell out of me in the beginning, that the stack grows downwards. I'm like, what does that mean? And what that means is when you add something to the stack, the memory location it is added to gets smaller. So hypothetically, the stack pointer here was at memory location 100. If you push something onto the stack, it would now be at memory location 99. So the stack grows downwards. And you would have seen in our assembler, we had .text to say, hey, this is a code section, and we're going to put our code in there. There's a bunch of registers, but to start off with, let's look at some simple ones. So the RSP is a pointer to the stack, the top of the stack, which is actually at that bottom. So this dotted line underneath stack would be where the RSP is pointing at in this example. The current instruction that's being executed is what RIP is pointing at. We looked in that example at a register called RAX, which is where the return value sits. And then there's, if you want to pass arguments to stuff, the first argument's an RDI, the second argument's an RSI, the third argument's RCX, RDX, etc. Now, there's a couple of other registers, but for simplicity's sake, we're just going to start with those ones. If you've done x86 assembly, those might look familiar, except they have E's on the front. So ESP is the 32-bit reference to the stack pointer, and then RSP is a 64-bit reference to it. We'll get into that stuff a bit later. All right, and then we've got some instructions. So these are the things that tell your computer what to do. So push and pop, add things to the stack. Push, you push something onto the stack. Pop, you take it off the stack. Oh, sorry, I've got phone calls coming through. Mov copies a value, or moves a value into a register or a memory location, or from a memory location to a register. So we saw in that example, we were moving the value 0 into RAX. LEA is a little like Mov, except it's different. If you're familiar with C programming, it's a little bit like dereferencing something. So what you're saying is take what's stored at this particular memory location and load that into something. It's kind of a relative thing. That you've got call, which calls a function, syscall, which calls a syscall, which is something on the kernel, or depending on what your computer operating system is, does magic things at ring 0. And then ret returns from a function. There are way more instructions, but these are just simple ones. So I just want to give you a simple view of, where am I here? Simple view of some registers and a simpler view of some instructions. And then here's what we covered, how you can build that simple binary. So AS to assemble it to an object file, and then LD to turn it into a binary. And my CPU is spiking intensely. I'm sure one of you are using some awesome Zoom rootkit. If you could just ratchet down the intensity there, that would be great. What is going on? Okay, let's see. So when I said that there's, okay, well, let's not jump into this. Let's go back into the Docker container. All right, so we looked at that really simple example, exit ret. So when you look at a normal piece of code, so there's some amazing lag. Can everyone hear me all right? Somebody on video, give me a thumbs up. Sweet. All right. So I'm going to look at some really simple code if my computer decides to cooperate. Okay, so this is a really simple C program. All it does is it defines a main function and it returns 0. Like, it's probably the simplest piece of C you can write. It is Zoom, unsurprisingly, spiking my CPU. Great, Zoom, thanks. So what you can do with this really simple C is you can ask GCC or Clang, depending on what you're compiling with, to generate assembly for you. I mean, that's what a compiler does, it generates the assembly. And so the way I've been teaching myself is effectively to just write simple programs, check what GCC generates with that. So the way you do that, GCC-S, then you give it the C file, and it'll happily generate an assembly for you. So the format I've used here is anytime that there's code, I just put GCC on the front with the dot, even though it's a .c file, so that we don't end up overwriting some of the simpler issues if you're using the Docker container. All right, so if we go check GCC exit ret-.s, which was automatically created by GCC, you can see there's a whole bunch of stuff in here. The good news is you can, like, a lot of it's not really important to understand what's going on. So we don't need the file. We need the text section, we need the global, we don't need the type thing. I'll briefly cover CFI later, but it's effectively how it handles understanding what's going on between function calls in the stack when you aren't doing the epilogue and prologue here. So if you delete all of that stuff, this is effectively what got generated by GCC. So you can delete that CFI stuff. So we can compile this in exactly the same way, hand assemble it, and if you want to, not compile. So we can call it GCC exit ret.o, GCC exit ret.s, and then we can do LD-O, GCC exit ret, GCC exit ret.o. So those same things. We've now got a binary called GCC exit ret, and we run it, we get the segmentation fault. Now, the main difference between this file and the one we looked at before is the inclusion of these instructions here. So what those instructions are, it's kind of the standard epilogue and prologue to push the base pointer onto the stack, preserve the previous base pointer, and then put it back on just before you return. So you can kind of follow function calls. It turns out that you can actually optimize these out. Modern compilers aren't human beings, and use that CFI stuff to unwind frames. And so these are the actual instructions which are executing. And so what you'll notice is that looks almost exactly the same as the exit ret S we looked at earlier. One of the differences, though, is it says mov-L rather than mov, and it says EAX rather than RAX. So what mov-L is, it's a variant of mov which moves along rather than a. So mov there, in the first one, we'll try and figure out what you're referring to based on the register name. So mov-L is saying specifically make it 32 bits and use the 32 bits of that RAX register rather than EAX. And because 0 is what we're storing in there, that's more than enough to hold that. And then we just return. So that general method of using GCC to compile really simple code into assembly is what I've been using to try and figure out what's going on. So the downside of that is you end up not really understanding the fundamentals. You're kind of hacking at it and reversing stuff, but I think you can really quickly get practical insight into what's happening. And then truthfully, I sort of find it quite difficult to find decent references which are explaining the fundamentals at an x86-64 level. So you can go and find lots of comp-sci stuff on toy assemblers or old school assemblers. There's quite a lot of stuff around x86, but x86-64, it's a lot more dispersed. In my, simple Googles, maybe somebody's got a great reference. Okay, so the next thing I want to introduce you to are syscalls. So the reason we're getting this segmentation fault when things exit is because we aren't exiting cleanly. Now, normally when you look at assembler, like online, a lot of times people will just have a ret. And actually, when we saw GCC generated that stuff, it just had a ret to return. So GCC's own generated code was seg-faulting. And the reason for that is normally you'd link with libc, and libc puts a bunch of stuff, well, and dynamic linker and libc put a bunch of stuff that happens at the beginning and the end. And one of those things is to cleanly exit using, eventually using a syscall to the kernel to exit. So we can skip all of that, and we're going to do a system call directly. So there's a bunch of different system calls. This one, 60, that's decimal 60, is the exit system call. And I'll show you some of the others and how to find them. And then I'm putting the value 1 into RDI, but I'm calling it DIL. So one of the things I want to show you here is you can refer to registers in different ways to deal with different parts of the register. So here is a much longer list of registers, and it's taken from that stanford.edu CS107 guide at the bottom. Oh, by the way, these slides are online in that GitHub repository. I'll show it to you again at the end. So you can see there's that RAX register we are using. If you wanted to refer to the lower 32 bits, it's EAX, lower 16 bits is AX, lower 8 bits is AL, and the higher 8 bits is AH. I think maybe that's wrong. Anyway, so we were talking about DIL, so you can see it's the lower 8 bits of RDI. And if you remember, RDI is the first argument that you pass to a function. So that's what we're doing here. If we switch back, is we're moving the value 1 into RDI, or at least the lower 8 bits. So 1 can be stored in 8 bits quite comfortably. So using DIL, which I'm really just using to introduce that concept, not because that's a particularly way you have to do it. And that 1 is the parameter that we're going to pass to the syscall, which is the exit thing, and that becomes the return code. Syscall calls the syscall based on what's stored in EAX, which is 60. All right, so everything else looks the same. The only difference here is there's an underscore before main. GCC seems to generate it without the underscore. Clang generates it with the underscore. It doesn't really seem to matter. Okay, so if I now do the same thing, so AS minus O exit syscall, no, exit syscall O, exit syscall assembly. I've created the object, and then I'm going to LD the binary. Exit syscall. Cool. It's created it, and now when I run exit syscall, it runs and it just exits, and we don't get a seg fault. And if I look at the return code, you can see the return code is 1, which is what we told that return code to be. Okay, so now we've, like, that's the simplest, this is the simplest assembly I know how to make that won't seg fault. And we don't need to link it to anything. We can, so if you look at the resulting size of that binary, there's the rest of the ELF stuff, but it's pretty tiny. By comparison, if you look at the GCC compiled version, which does that ret, wait, we hand compiled it. So if we do GCC exit ret on GCC exit ret.c, so when we actually compile that, you'll see that's a much bigger binary. That ELF file is a lot bigger. And that's because it's doing all of this stuff. So if you have a look using LDD on GCC exit ret, you'll see it's actually linked to stuff here. It's a dynamic linker using LD, and this is an Alpine box, so libc is muscle. So that's what it's linked to. By comparison, if we run LDD on our exit syscall, it's not a linked binary. It's not a dynamic binary. So it's just what it is. It's static binary. All right, so that exit routine you kind of need to bear in mind, because every time you're writing one of these things, you're going to write a hand exit yourself. Okay, so there's a lot more instructions. So remember, I just showed you a couple. You can jump to a label. Remember, main colon, that's our label. You can make arbitrary labels and you can jump to them. Compare will compare two things. So in assembly, you don't do an if. You'll compare two things and then make a decision based on the result, which you do with some modifier of jump. So JE is jump if it equals, JNE is jump if it's not equals, JG is jump if it's greater than, JGE is jump if it's greater than or equals. There's a bunch of variants like that. There's some mathematical things, addition, subtraction, there's division, there's binary manipulations. So if you want to look at some of the others, that's the reference I've been using. It took me a while to figure out the format that thing is presenting things in. But once you understand that, that's actually quite useful, a reference for looking these things up. Again, these slides are online, github.com/singe. If you look at the top repository, the x86 workshop, you'll see there's a slides.pdf in there. All right, and then if you notice, I was using mov in the beginning, and then we were using mov-l. So these are the different suffixes you can put on some instructions. Not every instruction takes every suffix, but B is going to be 1 byte, 8 bits, W, a word, 2 bytes, 16 bits, L, a long, 32 bits, and Q, quad word, is the full 64 bits. So a lot of the time, you'll see that stuff. Okay, I see some raised hands. So should we, let's have a quick question break.
Yeah, sure. Okay, I see the first question coming from H. Visage.
On my side, I only see one question from Ignacio.
Unmute myself. Okay, the question was, have you considered the LLVM CLang instead of GCC to look at the intermediate stuff?
Yeah, so instead of using GCC, using, I'm calling it Clang, it's probably the wrong thing, is how I actually started, because I've got a Mac, so I started off doing this stuff in macOS. But then I realized if I wanted to make it a workshop that you could all follow in, I should do this in Linux. And then I realized that actually there's quite a few subtle differences that you need to understand. So I'm just going with kind of the simple tooling here. But Clang also supports a -s, so you can check the generated assembly. Rust, you can generate the generated assembly. Go uses some weird-ass Plan 9 pipeline. That's not the same thing. So it can generate assembly, but it's its own assembly. But so there's quite a few compilers which can generate assembly for you, so you can kind of see what they're doing, which is kind of cool. I had no idea that was a thing. So it's made my life much easier rather than having to take the resulting binary and then reverse things. All right, so then instead of building really simple things, we can build slightly more complex things by linking with a linker. So passing in a dash dynamic linker and the location of your LD effectively makes it a linked binary. And I only learned this year. It turns out LD is actually a lol bin on Unix machines that you can use to directly execute a whole bunch of stuff, which I did not realize. All right, and then you can link in libraries. So -lc links in libc, so you drop the lib part. -e passes in the name of the function you want as the entry point. So by default, on normal compiled things, that entry point will be _start. So if you're going to make it something like main, you specify in -e. So that error we've been getting saying, I'm just going to make some assumptions because you're not telling me what it is. So that's a slightly more complicated string. So let's see what that looks like. All right, so before we do that, what I want to do is look at exit import.s. So here, what we're going to do is we're actually going to call a function that's imported from libc. So all of this should look familiar, .text, global, main. Here I've used mov-q instead of mov-l, and so that means I've got to refer to the 64-bit with register, so that's RDI rather than mov-l and EDI like before. And then I just do a simple call _exit. So this is one way of calling imported functions. There are other ways of calling imported functions. There's quite a lot of ways. In general, assembly gives you enough rope to hang yourself with. So this quite simply is going to do that and then look up the location of this function in libc. The link is going to link in libc, and it'll handle looking up that function and calling it. And if you then use something like GDB and step through it, you'll see that that's like a whole bunch of stuff that it ends up doing. Okay, so here, if we do as -o exit import.o exit import.s, and then if we try to just do the simple link that we did before, exit import.o, you'll see it gives us undefined reference to exit. Doesn't know what exit is, so it can't call it. So this is where we need to say, okay, well, that's a dynamic linker. This is Alpine, so it's in lib ld muscle. And then I'm passing it -lc, so link against the libc thing. So now when I run it, it doesn't give me that error, and I can run exit import, and you can see it exits. And if we look at the return code at 0, which is what we were moving in. Now we can run LDD on that binary, and you can see, okay, I didn't know it does that, but it's a dynamic binary that's calling that stuff. If you look at the size of exit import, you can see it's much bigger than the 400K or 4K we were looking at before. It looks a little bit more like the GCC binary. So to make your life easier, instead of doing all this stuff, in the build directory, I've provided two things. One is a makefile. So makefiles are dark magic that I don't really understand. The hardest part with this makefile, which I almost blatantly copied from somewhere else, was realizing it had to be a tab, not spaces. And I pretty aggressively changed things from tabs to spaces. That shows the depth of my ignorance here. So what this makefile does is it will do that. So there you can see that linking command in there, and it'll create the -o files using AS, and it can delete that stuff for you. Now I've already aliased make to that, which is a terrible thing to do, but for the simplicity here, copying makefiles around is a bit of a pain. So when I run make, it points to that makefile. So if we go back to exit, we can just type in make, and it compiled all of them for us. So we can see there's all of our binaries have been compiled, but now you'll see they're all linked. The whatevers were from testing earlier. They're all linked, so they're much bigger. And then if you want to clean them up, you can type make clean, and it'll delete the O files and the binaries and just leave you with your assembly. So that's one way to do it. What I've been doing is something slightly different, and like a real noob, I decided to make a script instead of a makefile. And it's just got some fun things that I found quite useful. So what this can do is you can use -R to say run the program after building it, so if everything worked. -C will delete the .o in the binary afterwards, so you don't have to worry about cleaning up. And then by default, it'll do the dynamic linking with libc, but if you want it not to, you can do -I no, and that stuff should work. It's not well tested. This is kind of just a playing around thing for helping me learn the stuff, when I'm handwriting it. So if I now do that against exit syscall.s, it assembles it, it links it. There you can see that link error. And then there's no output. It puts the output between these lines, drops the return code, gives you the size of the thing that was put together, and then it cleans it up. So I quite like this because it just means I can do things. And I've added in some other switches. -S will run systrace. Supposed to run strace, but it did not. Oh, because I put it in between a switch and a parameter. So here you can see it ran strace. So there it's running it, and there it called the exit syscall with 1. So you can check that it actually called that syscall. And then later on, you can also do -X to put things through XXD, but there's no output here, so you're not going to see anything there. You can do whatever you want. You can handwrite the instructions if you're following along. You can use the makefile. You can use my silly little play along thing. They're both in build. Compile -H will give you those switches. Otherwise, the makefile, you just type in make and make clean. Those are the two options. You can't even use it to make a specific assembly file. That'll give you an error. So it's because I'm a noob. So that's what the slide is talking about. Those are your two options. All right. So okay, no, I don't want to get to the. Do I want to get to this? Yeah. Okay, I'm going to come back to that. So I mentioned that there's a couple of syscalls. So we just use 60, which is exit. There's another syscall 1, which is write. So as in write to a file. If you want to look at 436 more Linux syscalls, you can get them from Linux 12L's main Linux repository in that file. You can either screenshot this now or get the slides from GitHub to cover that. Okay, so I'm going to come back to this. What we're going to do is let's make our hello world. So if you go to the hello world directory, see there's a bunch of stuff in there. And the first thing we're going to do is look at the hello world syscall.s in the hello world directory. Okay, so there's a lot more going on here. It looks way more complicated than it actually is. So the nice thing about assembly is it's super simple to understand when you're writing it. Like these instructions are really simple. There's no complex things. The horrible thing about assembly is it's very hard to understand at a whole. You kind of have to go through each instruction and figure out what stuff's happening. Okay, so here I'm creating a section within text that has 2 strings. And so what it effectively does is it sticks the bytes HELLO space in memory, but it gives us a label that I can use to refer to that address, that memory address that it gets put at. Same with world. Now I don't need to make 2 strings for this. I deliberately made 2 strings because I wanted to show you some things. So we could make this much simpler by only calling the syscall 1 and printing the whole string. So the way we call the syscall, if you remember with exit, we move the number of the syscall into RAX. So here the number of the syscall is 1. Now we're doing movq, so that means this full 64 bits, which is why we can refer to RAX, whereas before we were doing movl and EAX. We then need to, it takes 3 parameters. So the first parameter is what file it wants to write to. So standard out is file 1. It then wants the actual string that you're writing. And when I say string here, it's not a null terminated C string. It's just bytes in memory. And then it takes the length of the string that you want to do. So 1, 2, 3, 4, 5, 6 length. There is 6. And so I'll pass these as the parameters. So RDI is the first parameter, RSI is the second parameter, and RDX is the third parameter. So 1 for standard out, 6 for the length. This thing here is, so if you remember, LEA is like dereferencing. So it takes the contents of what's at that memory address and it puts it in there. No, actually I'm lying. This takes that memory address and puts it in there. And so this format here, .hello, so it's referring to that label we've got above there, as an offset from the instruction pointer. Is roughly, I'm going to mangle this as something to do with position-independent code and a way of using something it knows where it is in memory to figure out where other stuff is. And so that works to refer to the string. There's a couple of other ways. So Clang on macOS was using relocation instructions specific to AS. There's some hand ways of calculating some of these things, but I'm not going to go into that. Okay, and then here I do the second syscall, but calling world, and I deliberately wanted to show the range of the different instructions. So here I'm doing mov b to move 1 into the lower 8 bits of the lower byte of RAX. Here I'm moving a word, so that's 16 bits into the lower 16 bits of RDI. Here you kind of get the idea. B, W, L, Q. Wanted to show all of the lengths that you can use. Now this is doing almost exactly the same thing as this one, even though that order is different. So here I'm putting the third parameter in before the second parameter. It doesn't really matter as long as those registers end up with things. It's a little different from how things work in the x86 world. Excuse me. Then we call the syscall again to write, and then here's our exit syscall. I'm returning 1 for shits and giggles. Okay, so we're calling 3 syscalls, twice write and once exit. Okay, so if I use my compile, I'm going to say -rc, so actually run it and then clean up. I'm going to pass it hello world syscall.s. And here you can see it output hello world. Oops, resizing my window. Gave us our return code of 1. Awesome, that worked. So that's how we can do hello world. Now, much like with the exit stuff, instead of using a syscall, we can use an imported libc function. So if you have a look in hello world, I think it's print. Let's use puts. Hello world puts.s. So same thing. We're putting the string hello world in there, except this time I'm putting it in one place rather than 2. Effectively, this ends up with the exact same layout in memory. I just don't have a label pointing at W because it puts those strings in memory next to each other anyway. Then here, this looks familiar, LEA on that string, except now we're putting it to RDI because puts takes 1 parameter, which is the string that you want written, and then we call puts. So now, instead of doing underscore puts, so if you remember with the exit thing, we had underscore exit. Now we're saying puts at PLT. So the PLT is the process layout table, procedure layout table. I think it's procedure layout table. My inability to remember that should give you an idea about how well I understand that. But it's basically more magical linking relocation magic to call a linked function. So here we're then adding 0 to EDI, and we're calling the exit function. So we're calling 2 functions, puts and exit, which are going to be imported from libc. So this is way simpler than the syscall stuff, but what ends up being executed is way more complicated. Okay, so if I do build, compile, run and clean hello world puts, yay, we get hello world return code of 0. I'm just changing the return code, so you believe me, they're not completely made up. And by default, this got dynamically linked, so you can see it's a bigger binary. If we try and specify don't dynamic link it, just raw it, you'll see we get an error saying undefined reference to puts and to exit because those are imported functions. So we need to use the linked one. Okay, so we looked at how to do it with a syscall. We looked at how to do it with an import. And here's a slightly more complicated one using printf instead of puts. So if you're familiar with C, printf takes a format string, so %s just says print the string. So we've now got two strings in memory, hello world and the string. We put both of those into the two parameters, so RDI first parameter and RSI second parameter. We then, it's not a vectorized, yeah, I think we need to do this because it's not a vectorized something. I don't really understand what that is, but you have to set this to 0. So XORing a register against itself will set it to 0 because something can't be true while the other is false if it's the same thing. It can't be two states at once. So it's going to be 0. And then we call printf PLT. And then here we're just taking the return code of that, sticking it as the first call to exit PLT. So it's almost exactly the same thing as the puts. It's just a slightly different function with different parameters so that you can get a feel for it. And if we do compile, run hello world printf.s, it says hello world. And the return code here is 13 because that's what printf returned when it exited that function because it printed 13 characters to the screen. Okay, so that's ways you can do that thing. If you look in here, you'll also see there's a couple of GCC things because I want to introduce some compiler optimizations of the way compilers do things. So if you look at GCC hello world puts.c, this is really simple. No, not puts.c. My Zoom is blinking at me. Should we do question time? Yeah, let me take a break here. Does anyone have questions at this point? So if you want to ask a question, go to participant and then click raise hand. Then Michael Higo will unmute you so that you can ask a question. All right, cool. Are there any questions in chat that I missed that I should be asking? Lekker. All right, sweet. Okay, so GCC hello world.c is the one I want to look at. No. Yes. Okay. So if we look at GCC hello world.c, I made this a little more complicated because I want to look at what happens when you sort of declare some variables in memory and what goes in the stack. So here we're defining two arrays of char. So hello world and the format string. So that %s is a string, %d is a decimal. Giving it a number, 42. And we're saying print that format string, that variable, and these two variables, and return 0. This is an overcomplicated way of doing this. The reason I'm doing it is because I want to show you when we pass that to GCC with the -s, it will generate this here. So I've stripped out the CFI calls and things that would normally be in there. So those things that we don't need. So you can see just the specifics of what it's doing. And what you'll see is it's doing things like -16 RBP and -8 RBP. And so it's worthwhile spending a little bit of time talking about the stack, how the stuff's done. So there we go, the stack. So we mentioned earlier that you've got this thing called the stack, which the memory addresses go down as you add to it. So if you add something to the stack, the memory address of the stack, the top of stack pointer will be lower than it was before. And when you call into a function, the stack looks kind of like this. Well, not sort of at the end of the function based on what you're using. So you'll notice it was talking about RBP minus things. So what that's effectively doing is saying the RBP pointer over there, we can refer to offsets from that to effectively allocate space for variables. One of the things here is, let me switch back. Whenever you look at how to do x86 programming, that like people always have this prologue, push Q RBP, mov Q RSP RBP, and then at the end, pop RBP somewhere. I don't see that there. Anyway, but like I said earlier, actually compilers will optimize that out a lot of the time because they aren't human beings doing it. They rely on CFI to do the stack unwinding. So if you compile with any compiler optimizations like F, omit, frame, pointer, and then we give it GCC hello world .c. So if I compiled that, then we're going to get something that looks like this. I'm not doing it because I don't want to remove all of that stuff again. So here's that exact same code compiled with a mid-frame pointer. And what you'll notice is now there's none of that RBP stuff. Plus, it's now referring to things as offsets from RSP rather than RBP. And it's referring to it as positive values. So what that's doing is actually what was in that picture on the right here, is instead of saving the old base pointer onto the stack and then when you're done putting it back onto the stack so that you can kind of unwind functions, you can save yourself 3 instructions by not doing that. So it's a compiler optimization. There's this dwarf standard which has then used CFI. So when I was looking at this GCC generated stuff or stuff that had been compiled in other places, you didn't have this nice stack epilogue and prologue. So I think it's good to just get comfortable with that not necessarily being there. And so the other difference with x86-64 is when you get call into a stack, or when you call into a function, the stack layout has a thing called the red zone, which is some bytes that you can use to store local variables, some stack space you can use to store local variables or do some local things in registers. No, in memory, in stack. Well, getting myself confused. But it'll get trashed if you make a function call. So initially, when I was looking at GCC generated code, I was using these RSP minus, negative offsets from RSP, which is storing stuff in the red zone. Then I'd call something like printf, and instead of printing out hello world, it would print out gobbledygook. And I was scratching my head around this, and then somebody on Twitter helpfully pointed me to the fact that in x86-64 you have this red zone, and in x86 you don't have this red zone. And that made a lot more sense. So in the code that we're going to look at in a moment, because we're making a call to printf, stuff that's in the red zone will get trashed and wouldn't work. So instead what it does is it allocates stuff not in the red zone for variables. So if we go look there, what it does is it starts off, so we're subtracting values from the stack pointer. So we subtract 40 bytes from the stack pointer. We're subtracting because the stack goes downwards. And then, so here we're loading that string LC0, which is hello world, into a register RAX. And then it's putting RAX into memory at 16 bytes positive offset from the stack pointer. So the stack pointer is here and saying go back 16 bytes and write that. Then later on, we're putting the format string, the format string into at 24 bytes offset from the stack pointer. So in the stack layout, you'd have your format string, and then you'd have the string that we want to actually write. Then you'll also remember there was that integer 42. So it's storing that at 12 bytes offset from where the stack pointer is. Now there's plenty of space for that because we gave ourselves 40 bytes. So later on, when we clean up, we need to remember to add those 40 bytes back to basically clean up our stack space. And yeah, so that's kind of how variables get done on the stack. And the other thing to bear in mind is you need to align the stack. I'm not really sure why we align the stack. I'm sure there's somebody on this call who knows, is smarter than me. But there's kind of this assumption that you would be doing this push RBP prologue stuff. So it needs to be 16-bit aligned. I think 16-bit aligned. So, but it's off by 8. So you always have to, if you're subtracting here, it needs to be 8 and then increments of 16. So you'll notice 40 is 2 increments of 16, as in 32, plus 8. So I've actually been writing it just to make things easier for me to understand as take 8 off RSP for our stack alignment, and then how many bytes do I need to store memory in. Now, you don't have to use all of those bytes there, but you do need to align it. Okay, but this is the GCC generated code. So I wanted to show you what that looks like, that you can actually understand what a compiler is doing when you look at this. And then similarly, if you use -03 optimizations, it's interesting to see what gets generated there. So you can see it's quite similar, except it's skipping all of that intermediary register stuff. It's just loading memory straight into the parameter and then calling that thing, which actually makes a bit more sense. So sometimes, you know, I look at the assembly that's generated, I'm like, why are you taking it from memory into a register and then from a register into another register? Why don't you just take it from that? Maybe it's because of some optimization, but then you compile the optimized code and you see it's not like that. All right, so that's the hello world thing. And then related to that, if we look at hello world syscall again, instead of doing an imported thing, instead of making a label in memory for a string, you can push raw bytes into a memory location. It's just much easier to be able to do, you know, let's make a string section and add strings in. So this is just showing you, you know, what it would look like if you're pushing raw bytes in. But the problem here is you need to kind of push the bytes into continuous sections of memory because you can only push in so many bytes at a time. Yeah, that's just out of interest if you want to look at that. Okay, so there's a couple of other things in here. So exit we've looked at, hello world we've looked at. So we've got functions, if statements, loops, and variables. I'm not going to be able to go through all of those, but if you want to have a look at them to understand how that stuff's done, I just want to give you an idea of that structure. So if we go into variables, what you'll see is I start off by writing really simple C code. So if we look at GCC int.c, it literally defines, you know, A and B, and then C adds those and it returns it. So it's something really, really simple. So I can try and understand that. Now we can then use GCC generate the stuff. What I've done is I've then turned it into the very simple resulting code from what GCC did, and I commented a bit here. So here we're using the red zone. So you'll see it's a negative offset from RSP. Because this is a leaf function, it's not making a call to any other parameters. It is making a syscall, but it's not a function call, plus it's the exit. So we can use the red zone here. So I don't have to allocate space. So here it's moving the value 1 into 12 bytes offset from RSP. Here it's using value 2 from 8. So that's effectively the A and B variables. What sucks is you can't name your variables. So this is just A and B we specified in the comment, but that's for convenience sake. Here we take A and we put it into a register called EDX. We take B into a register called EAX, and then we add EDX to EAX. The result of that is going to be stored in EAX. So take the value of EDX and add it with the value of EAX. And now we can move EAX into -4, which is where -4, which is where C is being stored. So you can see A is at -12, B is at -8, C is at -4. So we then return C. So we're saying take the value at C, move it into the register that's going to be our first parameter that we pass to this function. We're going to call the exit syscall, and then we syscall there. So that's what I've tried to do through this stuff. So now if you wanted to, for example, look at GCC char.c, here is defining some strings, or some character arrays rather. So there's character A2's got A and B's got B in, and then both has both of them in, and then it puts them. And you might ask, okay, why did I write this particular C code? And part of the answer is because it generated useful assembly when I put it through GCC, so I could actually understand what it was doing. If I did like a char star, something really simple, it would just do what we've seen before, where it creates a string section, and I wasn't learning anything more. So when I go look at char puts, which is the one it would have generated here. So now we're adding stuff to the stack. We're not going to use the red zone because we're calling into a function. So that stuff will get trashed. And you'll see there's some interesting things here, which I'm not going to go into too much detail yet, but it's referring to like the lower parts of the lower 8 bits of EAX, because we're only using that much with these arrays. There's a couple of things going in there. But so when you look at this, if it's the first time you're looking at ASM, you're going to go, I don't know what the fuck's going on. Excuse my swearing. But when you break it down piece by piece with the kind of understanding of what I've been talking about, you can sort of wrap your head around it and go, oh, okay, cool. I'm starting to see what it's generating. So that's why I break these things up into spaces. So the last two things I want to show you are loops. So if you look at GCC 4.C, so this is a simple C4 loop. Doing something stupid, I create a counter, and then I've got a for loop with I as the incrementer, and then I just assign it to the counter and I return that. Again, I'm just doing that because I want to generate some assembly, which is actually useful. So that's a really simple for loop, and this is a really simple while loop, which does exactly the same thing. It just does it in a different way. So here I'm defining a counter, defining I, while I is less than 5, increment I, blah, blah. What's interesting about this is these two will generate the exact same assembly. So the generated while.s here and for.s are actually exactly the same. So even though you're using different constructs in the underlying programming, well, not the underlying, the overlying programming language, the assembly that gets generated is the same because it's understood the same way. And here you can see the use of so the new stuff here is we've got jump. So when it gets to this instruction, it'll jump directly to here. Here we're doing a comparison. So it's saying compare the value 4 with what's stored at that variable location in memory. And if it's less than or equal to, jump. If it's less than or equal, then go back to start. And if it isn't, then run our exit syscall here. So loops combine this concept of jumping, comparing, and then conditional jumps, which can be quite useful to understand. And then if you look at, if we go to the if stuff, here it's just doing some, let me show you the code first, sorry. So here, A is 1, B is 2, and then does a simple comparison. If A is less than B, return 1, otherwise return 2. So if you look at the generated assembly, it's putting A into that memory location, B into that memory location. It does a comparison between the two memory locations, but it can't compare the two memory locations directly. It has to stick one into a register, so it can compare a register and a memory location. And then if it's greater than or equal to, go to true, and there's our return value. Otherwise, our other return value is defined up here. So you can switch it around. If you wanted to run this, you can make this 2 and this 1, and you'll see that it'll then give you a different return value. So that's the ifs. And then if string is doing something similar, except it's using strings. So you can see how does it do string comparisons. The string foo and bar in memory, so you can switch these around. And you'll notice it's almost exactly the same thing. It's just the comparison and jump conditional is jump if not equal to. So I'm racing through it a bit because I don't want to shortchange Shifty Mike. And then the last one is function calls. What am I seeing here? So with function calls, you can, sorry, I was just checking what's in the chat, it's just popping up on my side. So you can call functions. So here's a really simple thing. So here's our main function, and it just says call foo, and then take foo's return code and copy it into our return code, which is EDI, which is the first parameter to the syscall. And all foo does is it's moving 1 into EAX as in its return code and then just returning. And you'll notice I'm not pushing RBP here. I'm not adding stuff onto the stack. We don't even need to use a red zone because we're literally just pushing a value in there. So this is like the simplest possible function call that you can do there. Okay, so that's that's kind of the run through of the things that are there. I think it's a fun Docker container that you can just play with. Go look at the C files, generate the C code for yourself using gcc-s, try different optimizations. So the two optimizations let me switch to slides here to show you that I'm using most often are emit frame pointer and no stack canary. So the emit frame pointer is what we looked at with not doing the epilogue and prologue with the push RBP and pop RBP. And then for things where you've got strings, it'll add a stack canary in, which basically sticks a value on the stack and then make sure it doesn't get mangled by the end of the function. That can be pretty confusing when you're looking at the generated assembly. So it'll only do it sometimes. It's not going to do just simple integer stuff. So you can add that in there. And then later on, I was pointed to the Godbolt compiler explorer, which is super rad. So if you go to that link, it's a simple C program, int main return with those emit frame pointer and emit stack canary compiler optimizations in there for GCC. So you can type C code on the left-hand side, it will generate the assembly for you on the right-hand side. And then you can just change the drop-down based on what compiler you want to use. So if you want to see what opcodes or assembly different compilers put together, that's a really quick way to just switch between it rather than having to type all those files. So I think that's pretty cool. The stuff that we didn't get to, which I would have liked to, is you can examine the stuff that you've created. Probably the most common tool for that, or that I was using, is objdump, objdump. -D will provide a disassembly, and -J you can focus in on the section that you want. So if you do objdump -D as in disassemble -J.text, it will show you your code portion. So if we go to exit, if you remember, exit ref.s was that really simple mob and then return. So if we do objdump -D -J.text on, need to compile it, objdump -D -J on exit ret .text. What you'll see is there's our really simple instructions that are put on there. If you don't give it a thing to disassemble specifically, I should stop fat fingering. So if you do -D, it'll disassemble all. You can see the wider, the kind of the rest of the stuff that's in the ELF file. And because we've done a dynamic executable that's linked to stuff, you'll see there's a whole bunch of stuff that it gets added in into there. So you can look at what exactly is compiled into things. You can also use objdump to disassemble your object file, the .o file. It doesn't have to be the final binary. There's also readelf, which can give you some interesting insight. And then the thing that I really wanted to get to for helping you step through and understand what's actually happening is GDB, but there's not, unfortunately, time for that. So GDP is a complex beast all on its own. And what I've done in this thing is I've made a GDB init file, which has this really simple stuff in layout ASM and layout regs. And so what that means is when you run GDB on something, it automatically puts it into a nice thing where it gives you the registers at the top and the assembly at the bottom, which is a nice way to try and figure out what's going on with assembly. And so there's just some really simple instructions to get you started with GDB. There's lots, if you Google, there's lots of guides telling you how to use GDB. The mistake I made is, for some reason, GDB is super buggy on Alpine. So I was segfaulting more often than I was getting useful information. For some reason, I cannot set the breakpoint to be the entry point of a binary. I have to use the function name, which means if it's a strip binary and there's no symbols, then you can't, blah, 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 blah. So I had a bit of a nightmare with GDP. If you're doing stuff on Mac OS with CLang or anywhere where you've compiled CLang and LLVM, I quite like LLVM. It was a lot easier for doing some of the stuff. So I'm going to leave it there. Just some shout outs. Thanks. NetSpooky stuff is awesome. She's just done some amazing stuff, super helpful on Twitter. Then this guy, Nick DeSoliniers, that's not his Twitter handle. He doesn't have a Twitter handle, it seems. He produced some really good stuff, some write-ups on his blog back in 2014, which are really useful. And these people were just very helpful for dumb questions I was asking. And then there's some references here if you want to read some more on this or play with it. So I mentioned NetSpooky stuff. She's got this cool, quick intro to basically writing some ASM using syscalls and then modifying the ELF file to make it as small as possible. Some of that stack layout stuff I was talking about, you can read there. I mentioned CFI a couple of times as to how the Dwarf standard does some of that stack unwinding, and you would have seen I was deleting those CFI references from the GCC generated stuff. You can read about what that's doing there. If you're just confused by this whole assembly thing, so back in the day, people would handwrite assembly for this 6502 processor. This is a really nice intro just into what assembly is and how to write super simple assembly where you don't have to worry about bit widths. It's all really simple. And then I mentioned Nick DeSoliniers had written some cool stuff. If you wanted that, switch over to Mac O. This was a nice intro. And then NetSpooky's also got a really nice one for PE mangling if you want to switch over to Windows. There's subtle differences and not so subtle differences between all of those. So it doesn't necessarily translate from one platform to the next. Yeah, so that's kind of what I wanted to go through. I mentioned a couple of times to people who joined late, so you can get the slides. You can get the slides there at that GitHub repository. It's just at slides or PDF. And the Docker container I was using is on Docker Hub there, or the Docker files in that repository if you want to grab it. Yeah, so that's my bit. Does anyone have some questions? See, there is one.
Yeah, I've got a question from Ignacio. You're unmuted.
Yeah, thank you. First thing I wanted to say is great presentation. Thank you very much. This is really very, very good. A couple of decades ago, I was in a data quality program, and I had to get the best performance out of it. And what I used to avoid the compiler from generating the prologue and epilogue for a function was this naked attribute on the function. That gets you the same, basically the same thing as when you do this optimization, right?
I will absolutely defer to your experience here. I'm quite new with this. So yeah, that's useful. I'll look into that. So you'd write that in the assembly and you'd say this function should be naked. And did you get muted?
Yeah, it's naked is a C attribute. So you put it on the C code, and
okay.
Yeah, so it hints the compiler that only this function you want it without the prologue and an epilogue. So you can actually from the very beginning of the function just play with the registers and all this stuff.
Okay. Okay. Cool. Useful. Thanks.
Awesome.
Yeah, and I just I've probably said at least 20 things wrong based on misunderstanding. So I just hope this kind of gets you to the same level of not knowing what you don't know that I'm at currently. But I think it's fun to have been learning. All right. Are there any other questions? Should we have a coffee break and then let Mike set up? Awesome. Thank you. All right. So, Mike, what are you thinking? 5 minutes, 10 minutes?
Yeah, I'm happy to wait a bit. People can go grab some coffee. My slides, I think, should take about 30 minutes or so. So don't need too much time.
All right. I don't want to keep people waiting if they've got commitment. So let's just make it 5 minutes. So I guess at 17 past, we'll start with your stuff.
Cool.
I'm going to stop sharing.
I will, well, everybody is away getting coffee and stuff. I bought this super gimmick. I'm going to get started. Let me get onto the screen sharing business. Okay, hopefully this is sharing my PowerPoint slides. If anyone does not see my PowerPoint slides, please let me know in chat, but I'm assuming that it's working the way it's supposed to. Can everyone hear me? Great. Cool, sorry about the lighting. I don't actually have a light source that can show my face, but you should not be looking at my face anyway. I'd recommend the slides. They have pictures and they're just generally better to look at. Cool, so when Dominic posted the thing on Twitter, I was in the early stages of designing and building a speed sensor for my bicycle. And it was, yeah, I'll get into the details of it, but this is basically just I guess a retrospective, a teaser for microcontroller development stuff, because I don't think it's as scary as it looks once you get a little closer to it. And I just generally want to talk about it because I get excited about making stuff. And it would be cool to see more people making these kinds of things. I guess a significant percentage of the people here are, they develop software in some form or another, if it's actually software dev or writing tools. But yeah, it's hardware is a bit of a different environment. You still get to write code and you still get to design stuff, and you run into the same kind of issues. But the fact that it has a real world component gets me quite excited, and obviously adds some additional possibilities that you don't have with software. So yeah, I just want to talk about my journey and yeah, give some feedback on the process. I also want to let you know that my primary job is as a sketch artist. So I've hand drawn some of the diagrams in this presentation. It's a bit of an interpretive style, but you're in for a treat. So you can look forward to those slides. I think you'll enjoy them. Yeah, so the reason that I decided to build a Bluetooth speed sensor for my bicycle is because I like learning about new technologies and stuff, but it's kind of difficult if there isn't an end goal or a project to use it for. So this is a good excuse to fiddle with microcontrollers a bit, which I haven't done in a while, and also delve into Bluetooth stuff, which didn't go to plan, but that's okay. This is the real world. Not everything always works out. Also, the fact that I can't buy any new equipment, components or anything like that makes it a bit more interesting, because now I'm forced to work within the limitations of lockdown. I can't order stuff online. I can't go to the shops. I'm pretty much stuck with what I have lying around, which is not that much. So that kind of makes it more fun for me. And I suppose the end goal is also supposed to be exercise, since this is for a bicycle. But yeah, we'll see how that goes. So that is my bicycle. It has provided me many kilometers of joy on the road outside. I have a mountain bike as well, but it's not, yeah, that's for a different purpose for mountains, obviously. Not so good for training and indoor stuff. Yeah, and it's great. I really like it, but it is an outdoor piece of equipment, and outdoor is not somewhere I'm allowed to go currently. So I needed to figure out a way that I could use this inside and actually enjoy myself. So that was my initial attempt to use this inside. It was kind of a tongue-in-cheek, hey, I wonder if this will work kind of thing. It doesn't. Don't try this. If you have a treadmill and a bicycle, the treadmill is not big enough. It doesn't accelerate fast enough because you need to get up to at least 10 kilometers an hour in a short space of time to actually get the what's that gyroscopic effect in the wheels to get your balance. You don't get that on a treadmill. It doesn't accelerate fast enough. And I'm pretty sure that you will wear out the belt because there's a lot of concentrated pressure in just 2 spots. Not to mention it's a massive health hazard. It's not going to be very hard to make one wrong move and fall off, and the thing won't stop. It's a terrible idea. Don't do it. It doesn't work. You won't get exercise. You'll just get sent to hospital. So enter the cyclotron. This is a real name of a real product. It sounds very cyber, but the point is it is for indoor training. The reason it exists is so that you can put your bicycle on it and you can cycle inside without actually going anywhere but achieving the same exercise benefit. So it's really simple. These 2 pieces, hope you can see my mouse, basically the top 2 pieces can, they're attached to the axle of the back wheel, and then this adjusts the position of this whole mechanism, and your wheel runs along this roller in the middle. On the right hand side of the roller is I think it's a 1.5 kilogram flywheel just to maintain the momentum. And on the left hand side is an array of magnetic things which generate resistance, because it's obviously if it could just spin and you didn't have the resistance, you wouldn't be doing exercise. And that's the whole idea. So that's the cyclotron. It's an indoor trainer. Lots of different companies make them, and yeah, so that's how it works. So at this point, I have my bicycle on a trainer, which is cool. Now I can cycle to my heart's content inside without leaving the house. I can cycle in the middle of the night. It doesn't matter. I can watch TV. It's great. It's still not super entertaining because I'm not moving. So this is where things start to get interesting. Of course, I also bought it and it needed to be serviced, and actually, if I'm honest, I think one of the bearings is shot and the thing doesn't really work. But we're ignoring that because my current focus is to build a speed sensor. So move on to that. The reason that I want to build a speed sensor is quite simple. I want to make indoor cycling more exciting. And to do that, I want to use this app, which is called Zwift. So some of you might be familiar with it. It's basically a virtual reality cycling app. So you have an indoor trainer like the cyclotron and a speed sensor on your bicycle, and then you connect it with Bluetooth to your iPad or iPhone, and then you log into this app and you cycle. Some of the trainers are really fancy. I think they sell, I think the fancier ones are about 20,000 rand. They're proper expensive. I paid 800 rand for my cyclotron, which may have been a mistake anyway. But they will adjust the resistance as you go onto hills, and they'll actually accelerate the wheel for you if you're on a downhill, and it makes it super realistic. But that's if you're really into cycling and have lots of, you're making money from it. So that's the idea. I want to be able to join other people cycling around. The other cool thing about it being a virtual reality application is that, we don't have to be bound by laws of physics. You can cycle inside an active volcano because why not? Which is pretty cool. There's a couple of real life tracks. You can cycle around London or Paris or whatever, but you can also cycle inside a volcano, which is a nice little touch. The problem is if you don't have a speed sensor, you cannot do this because the app doesn't know how fast your bike is moving because your bike isn't moving. So that's where this whole thing comes in. So now I need to make a plan. Here is the artistry I was warning you about earlier. So the idea in principle is to make some kind of speed sensor that reads the speed from the wheel based on the period between each rotation. That will connect to a device that has Bluetooth capabilities. Obviously, it could be on the same device, but in this case, that is how it was going to work. And then that device would advertise itself as a speed sensor, and the iPad or iPhone or whatever would be able to connect to it, pick up the speed, use the app, cycle in a volcano, everything's great. So that's the general idea here. So there's a few options for speed sensors. Obviously, I could buy one, but I can't. So different approaches for reading speed, all of them use the same principle. The amount of time between, or that it takes for the wheel to complete one full rotation determines the speed. So if you know the circumference of the wheel, you know how long it took to complete one revolution, you know how fast it's moving. So the first option was to use a magnet and pick that up with a Hall effect sensor or reed switch. Two problems: I didn't have a Hall effect sensor or a reed switch, and the other issue is that I didn't want to. I didn't like the idea because the only magnets I had were hard drive magnets, and they're quite heavy. So with the rotational thing, it creates imbalance in the wheel, and that's another problem. The next option is an accelerometer, as in the picture. And basically, I think it has a gyroscope as well, but it's able to pick up its orientation, just like any phone or any other device with an accelerometer. Super simple concept. There's an accelerometer which is connected to a microcontroller which has Bluetooth capabilities and a coin cell battery. Actually really cool devices which can be reprogrammed to do other stuff, which is something I'd like to look into at some point. But as it stands, they sit on the hub of the wheel, and as the wheel rotates, they can pick up their orientation. Because it's so close to the center of the wheel, it doesn't create any imbalance, although they're not very heavy. And the last option is reflectance. I didn't have an accelerometer, so that's also out. Reflectance is using light. This won't work so well outside, but the principle here is to have so you'll have an infrared LED in this case. You can use a standard LED, but I want to use, for this example, we use an infrared LED. And then you measure how much of the light gets reflected. So for that, you obviously need the surface to alternate different amounts of reflectance or reflectivity. So in this case, it would just be black and white. So when the LED is shining on the black surface, then it doesn't reflect as much. And when it shines on the white surface, it reflects more. Simple. So because that was I happened to have the hardware for that option, this is what I went for. So the first thing, I decided to measure the speed on the flywheel. Two reasons for that. One, I didn't need to make any changes to the bicycle. Not that I needed to make much of a change trainer either, but it's just a bit easier that way. The other reason is that the trainer that roller in the middle will rotate much quicker than the bicycle wheel will. So I will get a much more granular readings. I will show it in a later slide. It just means my refresh rate is much higher. So I frequently have the current speed. I don't have to wait for the whole wheel to complete a full rotation, which introduces some delay, especially when you're at lower speeds. So through a very scientific method of aligning, not in this picture, but the valve cap of the wheel with that line and rotating it until the wheel had completed full rotations and the trainer had completed full rotations, I got this ratio of 13.2. So now I know for every rotation of the wheel, 13.2 rotations of the trainer flywheel. Super. This is literally just multiplication. So the next thing is the reflectance. So there's two parts to it. There's the LED, which creates the light to be reflected. And then there is the, it's called a photodiode or photodiode. Basically, you connect it to power through a resistor. And the more light that it is reflected into it, the more current is allowed to flow. And the basic principle here is that the voltage here will change as the light it is receiving changes. So if you look at the next slide, here's my picture of a strip of paper. So what I've done is I printed a strip of paper looking something like this, stuck it onto the outside of the flywheel, and then I have this emitter and reflector. I will look at questions in a sec. So what you end up getting with this change is every rotation you'll see here it's on black and here it's on white. And as it turns, it cycles. So effectively every rising or falling edge, one or the other, is a full rotation of the wheel. If we only look at one, and there's no reason we have to look at both, but if we only look at one, then it doesn't matter if the black portion is 50% or 30% or 49 or whatever. So basically some of it just has to be black, some of it has to be white, and then we can see this. So on the software side of things, we now have a sensor that has been built. You can see my artistry is improving. We have a sensor which outputs some kind of a square wave. And then inside the microcontroller, we need to pick up on either a rising or falling edge, doesn't matter. And when that happens, we use a timer to detect or measure the time between transitions. And obviously knowing the different values of the circumference of the wheel, circumference of the trainer, all of that we can work out based on the time elapsed, how far the thing has, well, how quickly the thing is moving. So that's the maths part. And then the output is at this point still unknown, but somehow we're going to communicate with this Bluetooth device and then be able to use this thing with my iPhone. So this is just some of the maths. I'm not expecting anyone to read this, but I just wanted to show that I did do some maths. I remembered how to multiply and divide and use powers, which I was super proud of. Basically, there's lots of parameters in here. For example, the 16-bit timer. I won't get into that, but basically the timer counts from 0 to 65,535. There's clock dividers and all kinds of stuff. I needed to make the timer count at a specific speed. So this is all the maths to figure out all of that stuff. There was also some figuring out to do in terms of, again, with the timer. If the timer counts too fast, then it's going to overflow before it picks up the next reading. So if you're cycling too slowly, you may end up with a limitation where you can't measure anything below 10 kilometers an hour, but your upper limit is 80,000 kilometers an hour, for argument's sake, which was this min period and max period thing. So I ended up, finding a middle ground, which covered all sort of reasonable speed you do on a bicycle. So now I have a conceptual design. You can see the black paper on here. If I start that video, you can see in slow motion changing between black and white. So now the implementation needs to start. I have a sensor, and yeah, like I said, it doesn't matter if it's half-half or 40-60, it just needs to be 100% black or white. So here's the sensor that I built. Well, to test that it actually works in principle. So the clear part is the transmitter and the black part is the receiver. They have quite a narrow distribution of light, if you want to call it that. There is a real term for this, but I can't remember what it is right now. So their side rejection is good. So being right next to each other doesn't really cause much of an issue, but I did put a piece of cardboard there just in case. The blue thing is a potentiometer or a variable resistor, basically just a knob to change my reference voltage. And I will show you in the next slide why that's important. But basically it just sets a voltage to a specific point and it stays there. So this is the first test on an actual bicycle on the trainer. As you can see, there's really nice square waves as it transitions between the black and the white. You can see quite a consistent dip every time at the top. That might be some inconsistencies in the color. I use an inkjet printer for this, and it's not very black, but it's dark enough that it works. So the reason for the reference is the reference is my blue line, and the point of it is to basically we want to see when the voltage is higher than that or when it is lower than that. I will get to the reason for it later, but basically detecting a rising or falling edge requires the voltage to move above or below a reference. So that's all that really means. The takeaway is that this blue line needs to be adjusted to be nice and central in the middle of this, the amplitude of the wave we're getting from the sensor. And the more in the middle it is, the better that will, the better that will be detected, and the less susceptible will be to interference. So this is what the sensor looks like. Very straightforward. Two little LED type things. One is an LED, one is a photodiode, and stuck together and wires running to the microcontroller. Simple. So now comes the magic. This is where we start going from the analog to the digital domain. In fact, this literally does that. So this is an analog comparator, and it's kind of a weird child of a digital and analog parent. And what it does is it takes a voltage on each of these pins, and it very simply says, if the positive voltage is more than the negative voltage, it outputs a 1 or a high voltage. So a high voltage, trying to think of a good way to explain this. Basically, 1 is a high voltage and 0 is no voltage at all. It gets a bit confusing, but a high voltage doesn't mean high, it just means positive or binary representation of 1. So that's all that does. And the idea here is that my reference voltage, so that blue line, will be connected to here, which means that every time the sensor output moves above or below that reference, this state will change. So the microcontroller doesn't actually read the analog voltages. All it does is pick up if the state of this comparator has changed. So in the greater scheme of things, this is what the whole thing looks like. So the sensor, you have the sensor, which is the sketch I had earlier, which picks up the different voltages, the amount of light that's being reflected, and emits different voltages depending on that. And then you have your reference, which is just so that you can make sure that those transitions are nice and clean. And those connect to the comparator, and they go out to something else inside the microcontroller. Now, just to basically drive home, this is inside the microcontroller. So from this point, we're now dealing with a silicon chip, and it's all software controlled. So the analog domain pretty much ends here, and the rest of it becomes C code and a little bit of magic. So yeah, this is just to illustrate that point. So you can see here's the reference voltage, which can be increased or decreased depending on the setting of the potentiometer, and then the sensor will give you this. so the way the software works, also quite simple. I'm using an interrupt-driven, basically means this just takes precedence. There is a main loop which has stuff in it, but as soon as this interrupt gets triggered, this takes precedence over anything else. And so basically what I do is detect any transition from high to low, so 1 to 0. And if that happens, then I record the timer period and I reset the timer to 0 and it starts running again. So this basically allows me to just measure the time. And while that's not happening, we're calculating the speed in kilometers per hour and outputting it via something to, at this point, our Bluetooth sensor, Bluetooth device. So that is a very basic, it was the first test to make sure that this thing actually worked. I'm going to see, there is actually a light. So you can see the sensor facing the wheel, with the flywheel with the white paper facing it. And then the idea is that the light will just change from red to orange depending on where in the cycle you are. So this video, I mean, it doesn't tell you much, but you can sort of see the wheel speeding up and then stopping and then starting again. So then I just had to check, make sure that at speed, everything was still working right, and that I was getting the readings that I wanted. So you can see it's nice, clean transitions if you zoom in a bit. And here you go to where I think I don't remember how fast, but I was trying to go fast. So I guess it was fast enough. But there's a nice, clean transition. So don't anticipate any issues with this. And at this point, I can ignore the analog stuff. This is just zoomed into one of those transitions, and you can see that it happens in less than a millisecond, which means that the reading should be quite accurate, up to a relatively high speed. I think 11 milliseconds was 50 kilometers an hour. So yeah, well, full period. So both parts of the wave, this worked up to 13 or something. But point is, we shouldn't have any issues at even 100 kilometers an hour, which I don't expect to be going on my bicycle. This is an interesting sort of digression, but I tried to use my phone as a reflective surface to trigger the sensor. And I woke the screen up accidentally by touching the screen. And it did this. And it took me a second to realize that it was the Face ID LED matrix that was blasting my sensor and creating this. So I just took a recording to have a look. You won't get anything out of this because much like my sensor, it's just emitting light. The way it receives it is where the smartness happens. I'm going to quickly take a break to look at the questions here in the chat. I saw Megalodon said using a regular LED as a receiver works for data transmission. That might be the case. I'm in a weird position where I don't really have regular LEDs, but for a different project, I happen to have infrared receivers and transmitters. So I just use those because they do work quite well for this. But yeah, I've heard that and I haven't tried it, but I will look into it. And the analog to digital conversion. So that's the reason I use the comparator is because I didn't want to do analog to digital conversion at all. So the comparator literally just spits out a 1 or a 0 depending on if the positive voltage is more than the negative voltage or not. Yeah. So I don't have to use a analog digital at all. I just use a comparator and it just gives me a binary yes or no, which is much more convenient to work with. Cool. So yeah, if anyone wants to ask questions, go ahead, raise your hand. We can unmute you. Otherwise, I will proceed with the rest of this. can't see the participants view anyway. So cool, I will continue. So either this has been very clear or very boring. Okay, quick digression. So I believe that microcontroller development is easy and quite fun, specifically because you get to delve into a real world element and actually see things happen. LEDs switch on, you can push buttons, you can use sensors, screens, all kinds of stuff. So I really like that aspect of it. Arduinos are fantastic, and I'm not trying to take anything away from them, but as somebody who is a software developer, in a sense, I got frustrated with Arduino after a little while because I wanted to do very specific things once I started to understand what I was doing, and it sort of felt like I was being restricted by the ecosystem, which is fair enough. It does. The idea is to simplify it to make it accessible and easy for people to use. So, wow, my video is freaking out. Yeah, so I quickly went into the C side of things, and it actually wasn't as scary as I thought. Having a bit of C background, yeah, basically you're just playing with ones and zeros and bit shifting a lot. But for example, this one of the forums for AVR development, one of the members there, this is their avatar, and it's a GIF of making a blinky LED sketch and compiling it and programming it to the device and running it. And it really is that simple. You could type what he typed in there word for word, I think, depending on the device, and you would get the thing to blink an LED. A lot of the stuff that gets in the way is just prep work and knowing how to use the tools and stuff. But once you have that, it's actually not all that hard. And I think more people should do it. So that looks like something quite terrifying. It's a block diagram of the processor that I was using for this thing, this project. And while it's kind of overwhelming, I only care about a few parts of it. So obviously the processor and the flash and the RAM, that's sort of a given. But then beyond that, I only really care about the analog comparator, the digital analog converter, which I'll get into later, and the timer and the SPI bus, which I intended to use to transmit for Bluetooth. So once you have figured out what you want to use, you only really have to focus on those parts. There's some stuff, obviously, you need to have an understanding of, but for the most part, you can just focus on the things that you're interested in. So as an example, this is just a quick run through of what the stuff looks like in the data sheet. It is the Bible for when you are developing with microcontrollers. It tells you everything you need to know. So it'll give a rundown of all the features. You can see all kinds of things you can switch on, which most of the time you won't need. Then there is a block diagram. Again, I've just circled and read the things I'm interested in. There's also 2 of them, which I don't care about. There's a bunch of different references, which I don't care about. I just want to use it more or less in default mode, which you can do quite easily. After that, cool, my drawing jumped the gun. There's a description of each section, and then a register description to show you, so yeah, basically how to change the parameters and make it do what you want it to do. So for example here, if you set these 2 bits to 1, 0, then you will trigger an interrupt on a falling edge. So basically when you transition from black to white in this example. So here you'll see this is the corresponding piece of code which does exactly that. It's all defined as functions not functions, but they're enums, most of them, just to make it a bit more readable. But what that actually translates to is shift 0x2 6 bits to the left. And basically you take all of these things that these settings you want to switch on. So I want low level interrupts. I want to enable the analog comparator. I want hysteresis enabled and interrupt on a falling edge. And you just all them together and write them to that register. So if you simplify it, basically this is what it looks like in hexadecimal in the individual parts. And then if you simplify that further, you're literally just setting an 8-bit value into this register, that's it. And if you take it back, this 8-bit value corresponds obviously to the bits you want. So hysteresis mode, this is set to 1, you enable it, high speed we're not using, etc. So you could just say this register is equal to 0x93 and you'd have the same thing. But obviously it gets compiled to the same thing, but for readability, you leave it like that. But that's as simple as it is. You basically figure out where the 1s and 0s go and you put them in place. So once I had this all in the digital domain, I had also enabled the analog comparator output on a pin so that I could see what the microcontroller was seeing. And I was able to use a logic analyzer to record that. And this was one of the reasons that I wanted to pick up the speed on the trainer, is because I'd have more granularity. If you take that data and you basically put it into a graph, this is the inverse of what it should be, because this, yeah, I won't go into the details, but basically you can see each pedal stroke and how the speed changes. And you can actually see there's a slight peak here on the second one. I say second one, but there seems to always be a group of 2, and the one to the right is, well, depending on how you group them, is higher, which is most likely because my right leg is stronger than my left leg. So it creates some other possibilities. I'm not going to go into data science. I just know that this is data and it looks kind of cool. But the average of this curve basically gives you your speed, which is quite cool. So I think I worked out on this bike, because it's a single speed, you're getting 40 readings every revolution of the pedal. So 20 readings per stroke, which is quite cool. I don't know what it's useful for, but I like the graph that it makes. So the next part was to make this into a Bluetooth thing. I decided to use this board, which was actually part of a potential B-Sides badge, which never came to be. And yeah, I wanted to use this because it had a bunch of examples in the SDK. It has Bluetooth Low Energy. It has what I needed to have to use it as the communication component of the project. So it has peripherals to allow me to communicate with it. Basically, all I want to do is make the value available to it. So if it wants to know how fast I'm going, I say, it can ask, and the microcontroller says you're going 10 kilometers an hour, and then it can report that value to the phone. Bunch of example code in their SDK. I was interested in the cycling speed and cadence sensor example. Unfortunately, the example code doesn't work in this case. Some of the examples did work, most of them didn't. And there wasn't great support for this particular board either. So I was hoping this would be one of the easier parts of the project where I just smash 2 pieces of example code together and it just works. But unfortunately, I couldn't even get the examples to run, even with the pre-compiled files that were provided. So that gave me some confidence that it wasn't my own fault. Yeah, same thing when I tried with my phone, I just couldn't detect anything. I tried some of the other profiles, that seemed to work, but yeah. So I had to decide to give up on the Bluetooth idea, at least using that route. Unfortunately, using what I have lying around at home limitation means that I don't have anything else I can use either. So I had to scrap the Bluetooth part, unfortunately, which also means I can't do the Zwift thing. Watch this space, I may figure it out, but for now, I just continued with the project. So at this point, the microcontroller knows how fast I'm going, but that's kind of lame because it can't tell me and it's going to forget. And it's kind of pointless. So it needs to either show me in some way, but I don't have any screens lying around. But we have so many peripherals that have not yet been used. If you look at the data sheet, there's just a huge list of things. And so many of everything. There's 7 timers and 7 serial ports. There's even an AES crypto engine built in, which interestingly makes it really hard to buy these things from the States because you've got to sign a whole bunch of documentation saying that you won't use them to make, I don't know, bad things. But the presence of an AES engine in hardware makes these things, hard to export from the US. Not that they're any less powerful than, more powerful than, anyway, we won't get into that. It's silly. So the one I was interested is the digital to analog converter. And the reason I was interested in this is because I have something that can take voltage and show it as a number on a screen, which is kind of what I'm trying to do. So there's no communication protocol or anything, but theoretically I could generate a voltage proportional to the speed I'm going and show it on the multimeter. So this is really straightforward. Basically what a digital analog converter does, it takes the 12-bit value that it has. The register is 12 bits. Well, it's 2 8-bit registers, but it uses 12 bits for data. And you write a value from 0 to 4095, and then it will output a voltage between 0 and the reference you've asked it to use. So the chip actually comes with a 1 volt calibrated reference. So I figured, cool, I'll use that because it maps nicely to, I can just map 1 volt to 100 kilometers an hour, which probably won't reach, but that seemed reasonable. And then it's a simple case of taking the speed in kilometers an hour, dividing it by 4,096, and I get my DAC value. So once I'd done this, I now had a way to get that information out of the thing. It's increased by a factor of 10. So when it says 120, I'm going 12 kilometers an hour. The slow refresh rate is obviously due to the multimeter, not due to the microcontroller. You saw on the graph how quickly it updates, but it gave me a hacky way to see how fast I was going. So yeah, that unfortunately was where it had to end because Bluetooth wasn't an option, but I wanted to get something that could at least show me what was happening inside. So hopefully I can figure out what's going on with that SDK and try and get those examples working. But yeah, that was the journey of me building a speed sensor in lockdown. I still can't play on Zwift, which makes me a bit upset, but yeah, at least I finished part of the project that was important and got to cycle a little bit. I'll probably keep cycling after this. It's good for my health. Cool. Thanks for listening. And yeah, does anyone have any questions? I'm going to stop sharing my screen now.
Doesn't look like there's any questions.
Cool. Yeah, does not look like. Yeah. I see Megalodon says maybe try Wi-Fi. That is an option. Just thinking, I do have, so the problem with Wi-Fi is that I can't, the phone needs a sensor and it needs to either be Bluetooth or ANT if the device supports it. So that's the only way I'm going to get my phone to, or my iPad to see the sensor reading is if I use Bluetooth. So unfortunately, I'm limited to that. There is a Zwift companion app. So if you use Zwift on your computer, then obviously it doesn't usually have those sensors, or often won't have, not the sensors, the peripherals, so Bluetooth. If you don't have it, you can use the companion app, which allows you to use your phone as a bridge between the sensor and your machines. So maybe there's something in there. Maybe I could look at that app, see how I can spoof values in it, and then forward those on. So that's the one alternative I did think of, but yeah, didn't get a chance to actually implement that. So for now, I'm just using a multimeter, which works well enough.
All right. So I think we said we'd go from 2 to 4, so it's 4:02, nearly on the dot. A huge thank you to everyone who took some time out of your workday to attend this. Really appreciate it. Hope it was useful. You might have missed in the beginning, Hex Coffee is just a fun community. Nobody owns that. So if somebody wants to do something like this in a week's time or 3 months' time, let's do it. I think we've learned some lessons. Maybe Eventbrite wasn't the best way to distribute the Zoom meeting, and thankfully we didn't get porn bombed. Yeah, if you've got feedback, super keen to hear it. Shifty Mike on Twitter, Singe on Twitter, or Dominic@sensepost.com. Just things that you think we could make it better. Big thanks to Angus and Megalodon for running interference on Discord. Really appreciate that. Yeah, thanks very much, everyone. I hope you have a wonderful weekend. Stay safe with lockdown and keep your sanity.
Thanks, everyone. Cheers.